Okay, so in the last video, I cruelly taunted you by explaining the basic concept of how this experiment is going to be done and then not giving you the results. This video is going to be the last one in the series, and we'll give you the results of the experiment. So just as a reminder, what we have is a situation where they create a Bose-Einstein condensate. They trap it in an optical trap, and then in this sort of optical guide, they'll give the atoms a push, so they travel down this guiding laser beam and into a focused green laser that creates a light shift in the states of those atoms that acts as a barrier potential. Right, the atoms going into that region would have to lose energy to enter, and it turns out the energy that they lose can be greater than the kinetic energy that they have from the push they were given to send them into the barrier. All right. At the same time, this barrier region contains two very close together laser frequencies that drive a Raman transition, a two-photon transition from the plus X state to the minus X state. That transition takes some time, and that passage of time is reflected as a change in an angle on this block sphere picture as the atoms undergo Rabi oscillations from plus X to minus X back to plus X and so on. So this is the scenario that's happening. What do the results of the experiment look like? Well, this looks like a set of pictures of the atoms where they separate the plus X and minus X states. So so here are some photos of the atoms. If they arrange to have the barrier not present, right? They can tune the overall frequency of that green laser so it doesn't shift the energy states, but still drives these Raman oscillations. You see all of the atoms made it to the far side of the barrier in the transmitted region. And there's some plus X and some minus X, which allows them to measure how much time did it take those atoms to cross that barrier region. This lets them get the Rabi frequency for the laser very directly. All right. The bottom set of pictures here are for the barrier being on, and there you see that most of the atoms are on the reflected side. Right, most of the atoms hit that barrier and bounced back and returned to, you know, in the direction that they came in from. Only a smaller fraction of the atoms have shown up on the far side of the barrier. And again, there's some plus X and some minus X. The relative abundance of those two tells you for those atoms on the far side, how much time did they spend inside the barrier region. Okay. They can do this and then work this out into a set of angles. So here's a picture of the block sphere picture. In the larger figure on the left, that's a three-dimensional rendering. Those points are meant to be, you know, near the surface of the sphere. It's kind of hard to see in 3 dimensions, so they broke it out into two different projections, one in the XZ plane and the other in the XY plane. So you can see those on the right. The picture, the upper picture is the rotation in the XY plane. That's sort of the along the equator of the sphere here. That coincides with the Rabi oscillation from the plus X state to the minus X state that's being driven by this laser. So measuring the amount, the angle that the state is rotated through there tells you how much time passed in that direction. And they call that, in the paper, they call that tau y, right? So lowercase Greek letter tau, subscript y, indicating that it's in the XY plane, all right? They get a time from that. They also have this projection in the XZ plane. And from that, they can get an angle change there. That's sort of the change of the polar angle instead of the azimuthal angle. From that, they can get a time there that they call tau z. What is that? That corresponds to what's called a quantum back action, which is this barrier doesn't just cause this Rabi oscillation and the Rabi oscillation and changing the azimuthal angle. It's also shifting the energy of the states. And if you go through a bit of math about this, you find that the plus z state, which is some combination of the plus and minus x states, that plus Z state has a slightly higher probability of making it through the barrier. Its energy is shifted in a way that makes those atoms more likely to survive, whereas the minus Z atoms are less likely to make it through. So that shows up as this change in angle in the XZ plane. All right, and that's a thing that's understood in terms of making measurements of these quantum states as they evolve, and so it's a measurement back action, and they can predict a time that's associated with that, and they can measure a time that's associated with that. So when we convert these to times, what does this look like? Here is a graph from the paper showing the measured times as a function of the velocity of the atoms that they shoot at the barrier. You can see the velocity ranges from about 4 millimeters per second up to a little over 10 millimeters per second. That's sort of the time scale that we were talking about. And the times are on the order of milliseconds, which is the time scale again that we estimated. So good job, back of the envelope estimation. So what's going on here? Well, the position of the barrier, right? The speed that corresponds to the energy of the peak of the energy barrier is about where this red line is, right? So that's the barrier energy. Atoms that are moving faster than that should have enough energy to get over the barrier. They should all make it through and just pass through with a kind of normal velocity. The atoms to the left of that red line have energies that are low enough that they should not be able to make it over the top of the barrier, and therefore, if they show up on the far side at all, they're showing up there because they've undergone quantum tunneling passing through the barrier. And then we have two sets of times here. These sort of orangey points are this tau y. That is the time inside the barrier inferred from the Rabi oscillations, looking at the change in that azimuthal angle. That tells you how much time they spent inside the barrier interacting with the light. And then the blue points are measurements of this tau z that shows the effect of this back action. And you see that increases as you get deeper into the barrier, right, where things get more quantum. Right? The tau z is basically 0 on the outside because it doesn't make any difference that the plus z states are a little more likely to get through if the barrier is low enough that all the atoms are getting through anyway. So, but there's a little bit of more of an effect as you go into the regime where they're tunneling, and then the increased tunneling probability for the plus z state makes a difference, and that shows up in the data. Crucial thing to take away from this is these points that are below the barrier are not at 0 time, right? There is, in fact, a finite time showing up there, which is something in the neighborhood of, 7/10 of a millisecond, right? So this is saying that according to these measurements, these atoms have spent about 0.7 milliseconds inside the region where they're classically not allowed to be. Right, and this is a measurement of that time that is very clearly distinct from 0. Right, so there is not a chance that those are atoms that are miraculously appearing on the far side without interacting with the laser at all. So this is the key result. They've shown that this tunneling seems to be taking a finite time. The sort of shaded bands here are the range of theoretical predictions that you would make for a model that is assuming something about how long the atoms take passing through. And you see that they agree quite nicely, right? Both the orange points and the blue points fall right in the range where you would expect them to, given the theoretical predictions. So this is the experiment that was done up in the Toronto group. This is the evidence they have that the tunneling takes a finite amount of time. This is in the same way that the Addo clock measurements aren't perfectly definitive. This is also not completely definitive. People who are really attached to the idea of this tunneling being absolutely instantaneous have arguments that they make that, well, what you're measuring here is something else. It's not really that the atom is spending any time inside the barrier. This is an artifact of the way that you do the measurements. And so that's an argument that people can continue to fight out. But for the moment, this is an experiment that is doing a job of measuring how much time do the atoms appear to spend inside a region where classical physics says they shouldn't be found? And the answer is a little less than a millisecond. So that's the payoff of all of this lecturing about quantum physics and atomic physics and lasers and atoms and interactions with them and laser cooling and all that stuff. And so hopefully this has been somewhat illuminating. You can go back and you can try to take a look at the research article if you like, or you can go and look at those at the press articles that are on the Nexus site for this module. And see them hopefully in a somewhat new light and be able to understand a little better what are the issues that are involved and what the people quoted in those articles are talking about. So, and that is the end of this module of Physics 100. That is the end of this section of the course and this series of video lectures. So I hope this has been interesting and enjoyable, and I will see you whenever.